Precalculus 4.7 day 1. We're skipping over to 4.7 and we'll pick up 4.6 after we assess some of chapter 4. So anyways, this involves getting the inverse functions of sine and cosine. And so we want to review the inverse function properties. And if you have an inverse function, you only have that if your original function passes the horizontal line test. For example, if you had y equals x cubed, this function passes the horizontal line test. It is a function that only hits a horizontal line once, so its inverse is a function. However, if you have just y equals x squared, it is a function, but it does not pass the horizontal line test. So without restricting the domain, its inverse is not a function. And so to have an inverse, the original function has to pass the horizontal line test. When you have an inverse, the domain and range switch. Actually, the point xy goes to the point yx. Ordered pairs on the original switch positions to be on the inverse. And how you show algebraically that inverses are functions is you have to do two things. You have to do the inverse of f of x and show it comes out to x. And you have to do f of the inverse of x and show it comes out x algebraically. And then graphically, the functions are reflections over the line y equals x. And when you reflect over the line y equals x, again, the points xy map onto yx. They change position, and that's why domain and range switch. So we are going to be looking at inverse cosine and inverse sine. And the notation for inverse sine, you will see arc sine or you will sine to the negative 1 of x. This is red inverse sine of x. Or you will see arc cosine, which is exactly the same as the inverse cosine written like this. And again, when it's written like that, that is read as the inverse cosine of x. So this is read arc sine of x, which means inverse. This is read arc cosine, and the other notations are read inverse sine of x and inverse cosine of x. So if we recall the graph of sine, we have pi halves, pi, 3 pi halves, and you should be able to just map these out. So sine is at 0, then up at 1, then at 0, then at negative 1, and back up to 0. And I'm going to go back to negative pi halves, and at negative pi halves we'd be at negative 1 because it's the same coterminal angle as 3 pi halves. And so if I think about the sine graph, I'm just going to dot it because we're not really going for the sine graph, but it's involved in figuring out the inverse. There's my sine graph. And the problem with the entire sine graph, since it keeps on repeating its pattern, is it fails the horizontal line test. So therefore, we have to restrict this to an interval that is increasing or decreasing overall. I can't have an interval where it both increases and decreases because then it won't pass the horizontal line test. And so where we end up restricting is right here. Highlight that. Right in here. That is how we're going to restrict sine. So we have the entire range from negative 1 to 1, but we have an interval where it's overall increasing. So we're going to be using quadrant 4 and quadrant 1, and we're going to restrict that domain. So the restriction of that domain, so that its inverse is a function, is negative pi halves to pi halves. And then we get the entire range, which I need, negative 1 to 1 of sine. And so points, the 3 key points would be negative pi halves, negative 1, 0, 0, and pi halves 1. By the way, negative pi halves is about a negative 1.57. So positive pi halves is a positive 1.57. That's just a good value to know. And why I'm doing that is because the inverse switches x and y and switches domain and range. So on the inverse, the domain is -1 to 1, and the range is negative pi halves to pi halves. And so if I think of this as -1 and here is 1, then 1 would be here and pi halves would be about up here, because we're going to have on a range up to 1.57, and if this would be -1, then about here would be a negative pi halves, approximately. Oh, negative 1.57. So it's good. You need to know the decimal values to get this to map out right. So if these are on x sine of x, then on x inverse sine of x, we have all these ordered pairs. So -1, negative pi halves, 0, 0, and 1 pi halves. Again, this is about a negative 1.57. This is about a negative 1.57, or excuse me, positive. And so if I go to plot those, I'm at -1, negative 1.57, 0, 0, and to the right one and up 1.57. And when you draw this, it's reflections over the line y equals x. And so what happens is over on the original, you're concave up. When you reflect it over the line y equals x, you get a function that's concave down. And so that needs to be shown. So on this, it comes up and is concave down on this interval. And then on the interval from 0 to pi halves, since it is concave down, when it reflects over the line y equals x, that line y equals x would be somewhere in here, it becomes concave up. And so there is your graph of inverse sine of x. And it's going to be really important to understand that the range of this, the output of this, the y output, is always between negative pi halves and pi halves. So there is the graph. You need to get the concavity right and know how to graph those 3 points to be able to graph the inverse sine. Then we have the cosine graph. And the normal cosine graph starts up at 1, and then at pi halves, you're at 0. At pi, you're at -1. At 3 pi halves, you're at 0. And at 2 pi, you're back at 1. And if I go back to negative pi halves, you would be at 0. So the cosine graph, which you should just be able to sketch that out, no problem, no hesitation, right there, would look like this. If I don't restrict the domain on cosine, its inverse does not exist. I cannot use negative pi halves to pi halves because I don't have an interval where it's always increasing or always decreasing. I have an interval where it increases and then decreases, and it would fail to pass the horizontal line test. So on this graph, we are going to be using from 0 to pi as our restriction. So that's what we have to restrict to so that I get an overall, the entire interval is decreasing. And I also get the range to be from 1 to -1. I get all of the outputs of cosine. So I'm going to restrict again the domain, but it's a different restriction because I want an interval where this is always increasing or always decreasing, and I want to include quadrant 1. And to do that, I need to restrict my domain from 0 to pi. And then my range is -1 to 1. And once again, the points on there that I would be using for x and cosine of x would be 0, pi halves, and pi. And the cosine of 0 is 1, cosine of pi halves is 0, and cosine of pi is -1. So now when we go to graph the inverse, the inverse on that, the domain and range switch. So the domain is -1 to 1, and the range is 0 to pi. So this inverse function is above the x-axis except for at this 1, 0. And these three ordered pairs all switch in terms of the points on the inverse. So x and inverse cosine of x, you get 1, 0, 0 pi halves, which is approximately 1.57, and then -1 pi, which is about 3.14. And when this gets reflected over the x-axis, since this original part is concave down, well, it doesn't work quite that way. Sorry on that. So when we go to graph this, you have to plot those points. So you are at 1, 0, 0, and 1.57 pi halves. So that's 1.57 approximately. So 1's about here and maybe a little bit lower. 1's about here, 2's about here, and then 3's just slightly below the pi. And then -1, 3.14 is up here. And watch the concavity on that because you need to get that concavity correct. So that shape has to be correct. I get people who draw it more like this. And that won't get credit because that's the wrong concavity. So to the left of the y-axis, it's concave up. To the right, it's concave down. And it needs to look like that. All right, so those are some things. And again, what's going to be really important as we do inverses is that the output on inverse cosine is restricted between quadrants 1 and 2. Those are the only possible outputs of inverse cosine. So also notice that the range are what the angle measures were. So this range were the angle measures. And so on this inverse, you have to give the unique number. There's only one possible output of inverse sine, inverse cosine, and it has to be in the correct interval. And so when I see inverse sine of theta, first of all, I'm thinking of this. This is an angle measurement. This is an angle measure. This is an angle measure. And the output must be in that restricted range for inverse sine. And so you need to remember, how did I restrict sine? I restricted it from -pi halves to pi halves, so I had an increasing interval, so that becomes the range. So the output of this has to be between -pi halves and pi halves. If I think kind of on a unit circle, we're going to go backwards this rotation, a -pi halves, and forward this rotation, a +pi halves, so that my output always is the quadrant 4 or quadrant 1. And to get to quadrant 4, we're going to swing counterclockwise and have values between 0 and -pi halves. To get quadrant 1, we're going to swing counterclockwise and have values between 0 and pi halves. So the inverse function is a unique number in the correct interval. So we never go around this way to get quadrant 4. Our angle isn't going to be 11 pi 6 or 7 pi 4s when we have inverse sine. it's going to be from 0 to negative pi halves. We would use negative pi fourths, or we would use negative pi sixths, or we'd be using negative pi thirds as our possible angles. All right, so on inverse cosine, again, the output of that is an angle measure, or that's what it gives. And the output is restricted. And it is restricted to 0 to pi, the range of inverse cosine. And so when I'm thinking about on the unit circle, I'm going to be going from 0 to pi halves to pi. Those are the only kinds of angles I can have out of inverse cosine. So it might be the pi sixths, the pi fourths, the pi thirds, pi halves, or 2 pi thirds, which is an output you can have for inverse cosine but not inverse sine, and then 3 pi fourths, or 5 pi sixths. So those are going to be the outputs of inverse cosine. It's restricted to those two quadrants, a unique number, only one possibility. All right, so when here on example 1, it says find the exact value of the expression. Remember, this means the exact same as inverse cosine of negative 1/2. This is a no calculator activity, and I'm going to ask to put your angles in radians unless otherwise specified. And so this inverse cosine, arc cosine of negative 1/2, is a unique angle between 0 and pi. And when I look at this, it is the angle between 0 and pi, inclusive. It can be 0, it can be pi, whose cosine is negative 1/2. That's how you should be reading this. It's the angle between 0 and pi, inclusive, meaning it could be 0, it could be pi, whose cosine is negative 1/2. And so you want to be thinking, if I'm on that unit circle, what angle between 0 and pi will have an x-coordinate of negative 1/2? And that's going to have to be a quadrant 2. And it is that reference angle of pi thirds. And so this rotation is 2 pi thirds. That's where I'd have a negative 1/2 and up root 3 over 2. This ordered pair would be negative 1/2 up root 3 over 2. So what angle has that x-coordinate of negative 1/2? And it is 2 pi thirds. That is the only possible angle that you can give me, because we are restricting the output between 0 and pi. So it's what angle is in the zone for inverse cosine. It's unique. Only one possibility. That's what we mean by unique. All right, so in part B, we have the inverse sine, which is on the outside. So the end answer, because this is the last thing you're going to perform because you're going to do inside the parentheses first, the end answer has to be between negative pi halves and pi halves. That's going to be the end answer. So what we're going to first of all do is take the sine of pi 6. And the sine of pi 6 is positive 1/2. Again, it's 30 degrees. I think about pi 6 being right here. This is root 3 over 2. This is up 1/2, radius of 1, unit circle. Here's that root 3 over 2, up 1/2. When this angle right in here is pi 6, or that 30 degrees. And so the sine of pi 6 is 1/2. So when I then want to evaluate the inverse sine, I have to have the angle between negative pi halves and pi halves inclusive, whose sign is 1/2. Well, in this case, because pi halves or pi 6 is between negative pi halves and pi halves, that is the angle. That is the answer. Because pi 6 is in the zone. It is between negative pi halves and pi halves. And the sign of pi 6 gives you the 1/2. And the inverse sign of 1/2 then is going to have to be pi 6 because pi 6 is between negative pi halves and pi halves. You might be going, well, isn't that how it always works? No. And so in part C, the answer to this is not 7 pi 6. Why? Because 7 pi 6 is not in the zone. It is not in the zone for the output of inverse sine. The zone is negative pi halves is less than or equal to theta is less than or equal to pi halves. That is the zone for inverse sine. It's not the same for inverse cosine. So I need an angle. Since arc sine is on the outside, my final answer has to be between negative pi halves and pi halves. 7 pi 6 is not that. So when I do this, I'm going to do the inside first. And the sine of 7 pi 6, again, the reference angle is 30 degrees. And the sine of 30 degrees of pi 6 is 1/2. But since it's in quadrant 3, it's negative. So I need the angle between negative pi halves and pi halves inclusive, whose sign is negative 1/2. So I'm thinking on the unit circle, I have to rotate clockwise. My possibilities are the 0, the negative pi 6, the negative pi 4ths, the negative pi 3rds, or negative pi halves. For any other angles, we'd be using a calculator. And why am I going that direction? Because the ratio is negative, and you don't get negative ratios in quadrant 1. So even though arc sine goes this way, since the ratio is negative 1/2, I've got to drop down and be in quadrant 4. And which of these would have a y coordinate of negative 1/2? Well, that would be your negative pi 6. That's where your y coordinate's negative 1/2. So the angle between negative pi halves and pi halves inclusive, whose sign is negative 1/2, is negative pi 6. So I'm going to do a U try. I'm just going to scroll up and U try to give me the value for this in radians. So I suggest that you pause it, think through it, see if you get the right answer. Check your understanding. This is a no calculator activity. Let's see how you did. So this becomes the inverse cosine of, and 4 pi thirds, right, rotates around here and comes down here where the reference angle is pi thirds, your pi thirds beyond half a rotation of pi. And so this ordered pair is negative 1/2, negative root 3 over 2. This is negative 1/2, and this would be your negative root 3 over 2 if the hypotenuse is 1. And the cosine is the x coordinate of that. So this is inverse cosine of a negative 1/2. So now you need the angle such that sorry, 0 is less than or equal to that angle is less than or equal to pi, because that's the zone whose cosine is -1/2. And so you have to think about, okay, the ratio is negative, so I have to restrict my answers in inverse cosine from 0 to pi halves to pi, including 0 and pi. That's where my angles have to be for the output of inverse cosine. That's the restricted zone. Well, cosine's not negative in quadrant 1, so I need quadrant 2 where cosine's -1/2. And that's going to be right here, which is at your 2 pi thirds. Because if I were to draw that triangle, and this reference angle would be pi thirds, then this is -1/2, while this is positive √3/2, and this is 1. And on the unit circle, that ordered pair is where the x-coordinate is -1/2. So the answer to this is 2 pi thirds. The output of inverse cosine has to be in the zone, which is 0 to pi, which is different than inverse sine. All right, so then if you do this on a calculator and I want radian measure to 2 decimal places, then make sure if I want it in radian that you switch. So if I go to Desmo Scientific Calculator, I've got degree or radian, I need to switch. And then if I go to functions, inverse cosine is, by the way, not 1 over cosine. That's not a reciprocal function. Inverse cosine of that 0.5 or is 1.047. So to do 2 decimals, 1.05. You've got to make sure your calculator's in radians. And that's a real number, so there's no degree sign on it. Then we have an inverse sine of -0.125. And so I'm in radians, function, inverse sine, and then -0.125 is a -0.13 to 2 decimal places. -0.13. So those are the values to 2 decimal places. Okay, so in example 3, use an inverse trig to write theta as a function of x. And so when I'm looking at this, I'm solving for the angle. This is a little more abstract because we have a variable. And so what I want to do is, with this being the angle that I'm referring to, this is the leg opposite, and this is the hypotenuse. And so I want to recognize, oh, what works with opposite and hypotenuse? Sine. So sine of theta is that opposite over hypotenuse. So that means sine of theta is going to be 4 over x minus 3. But I want to use an inverse trig function. So I want to apply the inverse sign to both sides. So I'm doing the same thing to 2 sides that I say are equal. And the inverse sign of sine of theta gives you theta, a theta between -pi halves and pi halves. So we'd write theta is the inverse sign of 4 over x minus 3. And we have used an inverse trig to write theta as a function of x. That's it.